Hi everyone, and welcome to your next lab. This week your lab is about calculating the mass of Jupiter using the orbits of its 4 moons. And before we get into the lab, I just wanted to kind of go over what these 4 moons are and what they look like. So of course, the system revolves around Jupiter. We all know Jupiter. It's the largest planet in our solar system. It is a gas giant, meaning it's made entirely of gas. You can see its great red spot down in the southern hemisphere, and this is pretty much what you would see if you were to look through a telescope at it just up in the night sky with no corrections. So then the first of its moons is named Io. This is a picture of Io. As you can see, it's a very metallic looking surface. It doesn't look like it has any water or anything on it. Io is the closest moon into Jupiter, meaning it has the shortest orbital period. Next out, you have Europa. Now, Europa is a moon that has an ice surface and we believe a subterranean ocean. And you can see this by all of these cracks across its surface. These are actually cracks in the ice. So this is Europa. Europa is the second out from Jupiter, meaning it has the second smallest orbital period. Next out, you have Ganymede. This is just an image of Ganymede. You can see it's a pretty heavily cratered surface. It's got some markings on it, some big splats where it's been cratered. Overall, it's just fine. It's the third out in our sequence of moons. And last but not least, you have Callisto. Now, Callisto is my favorite object in the solar system because of just how pretty it is. I mean, this is an actual picture of Callisto. And just a fun fact, Callisto is the oldest surface in the solar system, meaning that there's no active water or lava on the surface filling in all these craters like you learned about what happens on Mars. None of that's happening here. So it's the oldest surface, as you can tell by how many craters are on its surface. So this is Callisto. Callisto is the last of Jupiter's 4 moons. And I should clarify, these are the 4 Galilean moons. Jupiter more than likely actually does have more than 4 moons, but these are the 4 moons that Galileo discovered. And Callisto, like I said, is the furthest out of these 4 moons. So I also want to give you guys, before we start the lab, a cool way to remember the order of these moons, because it's probably something that'll come up on a test probably at some point. So progressing outwards, so starting with Io, the one that's closest into Jupiter, and moving out to the one that's furthest away from Jupiter, you can use the saying, I eat green cats, where I is Io, eat is Europa, green is Ganymede, and cats is Callisto. So it's just a fun fact. It's something one of my professors taught me. So now going into stuff about the lab. This lab is going to be very mathematics based. So remember back to the Kepler's laws of motion lab. You have Kepler's 3 laws, and Kepler's third law is this equation. The orbital period, p, raised to the power of 2, or p squared, is proportional to your semi-major axis cubed. And remember, your semi-major axis is half of the longest axis in your orbital ellipse. So Kepler's third law, and then if you combine that with a law that you see more commonly like in physics, which is Newton's law of gravity, F equals G, m1, m2 divided by r squared, where F is force, G is the universal gravity constant. M1 is mass of one object, m2 is mass of another object, and r squared is the radius between your 2 objects. If you combine these 2 formulas, you end up with this formula, which is what we're going to be using, or it's going to be much more applicable to our lab, which is you have p squared times m1 plus m2, remember those parentheses are really important, and that equals a cubed, where again, P is your period of the orbit or orbital period. M and M1 and M2 are masses. M1 is generally the mass of the larger object, meaning the planet in this case, and M2 is the mass of the moon or the smaller object, and A is your semi-major axis. Now we can further condense this down to what we're actually going to be using in this lab if we assume that your M1, which is your planet, is significantly greater than your M2, meaning your planet is significantly larger than your moon. Now, this would not be the case if we were looking at, say, a dwarf planet like Pluto, because if you look up images of Pluto and I think it's Chiron or Charon, I don't remember, they're pretty similar in size, so this assumption wouldn't apply to Pluto's system. But for Jupiter, the most massive planet in the solar system, it does. So we can assume that M1 is significantly greater than M2, and we can therefore basically just say M2 is equal to 0. I know it's quite a jump, but trust me, we can. Then our formula further condenses down to the mass of your planet is equal to the semi-major axis cubed of one of its moons divided by the period squared of one of its moons. So with this really clarifies how we're going to be able to use Jupiter's moons to find the mass of Jupiter. So then switching over, let's start looking at the lab. So this is just your lab activity module 11 page pulled up. You have quite a few pages. Most of them are normal. Again, you've got your PDF file, your Word file. This video will be posted here on the first introduction page. The new file that you have that you absolutely need, you have to download it, is this Excel file, because this has all your data in it, or your data. So you can pull this up. You can see that it has your observation step and your distance from Jupiter for all 4 moons. So it's fairly long. You just go ahead and click this little down arrow and click download. Or you can click download at the bottom of the page. Once you have it downloaded, this is what it should look like. Now, I'm on a MacBook Air, so if you're opening the Excel file on a Windows or a PC machine or a Linux machine, it'll look slightly different. And so the steps taken to make the calculations and the charts you need will be slightly different. But I can only show you what I have. So the steps I'm going to show you today are for a MacBook. The steps listed in the lab itself are for a Windows machine. So just follow those really closely as you can. So this is your Excel sheet. You have your observation step in hours in your furthest left column. Now what this means is this is from 0 to 2, that's 1 step. And it is 2 hours, meaning that, if I were to progress 1 tick mark on our x-axis, that would be equivalent to progressing 2 hours forward in time. Now, these are all paired with a distance from Jupiter in Jupiter diameters. Now, remember that when you have a circle, you have, very similar to like an ellipse, you have, you can draw a line straight through the center. And for a circle, because if it's a perfect circle, then no matter which way you tilt that line, it'll always be the same. So that full line from edge to edge is your diameter. Now, if you were to take from the middle to the edge, that would be your radius. So distance from Jupiter in Jupiter diameters basically means it's basically a distance of how far away these moons are. And you can see they actually get pretty far away. Like this one is at 2.3 Jupiter diameters away. So they're not right up close to it. So anyway, you have your data here in these 2 columns. This is what you'll be mainly working with. Then over here, you have a big chunk of text. And this is where you're going to be inputting all of your calculations. And then you'll be using these calculations to answer the questions in the lab. So It's incredibly important that you actually fill out this table and you don't just write down the answers in your lab without actually doing the math, because we will be opening these Excel spreadsheets and looking at your math and comparing it to ours to make sure that it matches up and see where you went wrong if you did. So just going over this really quick, this left-hand side is where you're going to be calculating the orbital period of your moon. So T1, T2, that's just time 1 and time 2. And then you're going to calculate that in hours, in days, and in years. And I'll go over how to do that, how to do all that in just a second. Then on this right-hand side, you've got the semi-major axis. So first you're going to calculate the semi-major axis in Jupiter diameters. Then you're going to calculate it in astronomical units. Now remember, we've gone over what an astronomical unit is, but just as a refresher, 1 AU, astronomical unit, is equivalent to the distance from the sun to Earth, basically. So then down here, you're going to be calculating the mass of Jupiter. And the formatting got a little messed up. You're going to actually start filling it in here next to the in solar masses. You're not going to write anything down here. This is what it should look like actually. On the last tab of the spreadsheet, it's formatted correctly. So you can see you've got your mass of Jupiter column. You're going to start filling it in solar masses. That's basically, you know, how big is it compared to the sun? Or how heavy is it compared to the sun? I can tell you it will never be 1. Because if it's 1 solar mass, then that means it is equal to the mass of the sun, which it's not. It's significantly smaller. And then you're going to calculate that for Earth masses, basically comparing it to how large it is compared to Earth. It's going to be very large compared to Earth, just so you know. And then we're going to be going over to how to calculate the percent error. So I will go over all that with you. But one last thing about the spreadsheet is down here at the very bottom left-hand corner, you have several tabs. You have one for Io, you have one for Europa, you have one for Ganymede, and you have one for Callisto. They all have different numbers, so it's important that you do all of them. And you record the proper values in the proper spreadsheet. So with that, let's take a look at the lab. Okay, so here's the lab. Mass of Jupiter, in big bold letters here. In your objectives, it says to also submit your Excel sheet with your lab. Again, obviously, yeah, you write down stuff in your Excel sheet, you don't submit it, we can't grade it. So please submit your Excel spreadsheet as well as the lab PDF or Word document. So some definitions: the Galilean moons, they were discovered by Galileo in late 1609 and early 1610. They're the 4 largest moons of Jupiter's system: Io, Europa, Ganymede, and Callisto. So that's just to clarify what I said earlier. Period, it's basically right, like the Earth orbits around the sun, and 1 period is 1 orbit, and it takes the Earth 365 days. For the moon orbits around the Earth, 1 orbit is 1 period, it takes about 30 days. And then graphically, it's the length from one peak or trough to the next. And I'll go over that and what that kind of looks like. So then amplitude, again, it has to do with the orbital graph, and I'll show you what it looks like. And then Kepler's third law of planetary motion, it's just kind of re-explaining that. So then this is the lab. It starts off giving you some background information about the moons and about their discovery and Galileo. And normally we would have you gather the data yourself from a simulator, and we would normally only have you do it for 1 moon and make the graph and then measure things. It takes a full 2 hours just to do 1 moon with that. We've set it up this way. You're going to do all 4 moons, but you've already been given the data. So I'm going to show you really quick what the simulator looks like, just to give you some background information about how we got this data. Okay, here I am. I'm back. I've got the simulator pulled up. I'm using the VLab software again, so you're all familiar with that. But this is what it would look like if you were doing it on the lab computers. You've got the calendar date down here. You've got the universal time at this moment. It's 0 hours, 0 minutes, 0 seconds, 0, 0, 0. You've got the Julian date, and you've got the data interval. So I would go in and adjust all these settings so that your data interval is 2 hours, but I'm not going to do that here just for brevity's sake. I'm going to click the zoom in button just so we can see things. So here you have Jupiter. Notice it's flipped, right? Because the way telescopes work is the images that you're seeing get flipped. Anyway, regardless, each of these yellow dots is a moon. So if I were to click on this moon, this is Io. So this one's Io. Click on this one's Callisto. This one way out here is going to be Europa. And then I have to zoom back out to see Ganymede, which is way out here. Now you might say, whoa, wait a second. I thought Callisto was the one furthest out, but Callisto looks like it's the one closest in, right? This is just a perspective thing because they're all in different places in their orbit. So Callisto's kind of in front of Jupiter, Ganymede's way out to the side. So Callisto is still further out than Ganymede. It just looks like it isn't because it's kind of in front of Jupiter. So then I'm going to zoom back in, and as I click next, the moons shift position. Jupiter changes. Now this is a 24-hour interval, so this isn't exactly what you would see, but you can see now the moons have all shifted positions. And so the way that we would get the data that we're using for this lab is we would look at your X and Y coordinates, and you would look at 3.65 east Jupiter diameters. And this is the number that we would actually write down, this one at the very bottom. So for Europa, I would say my time is 24 hours, so that's a couple steps in if we were going at 2-hour intervals. And I would say it is 3.65, and then east and west correspond to a negative or a positive. So that's how we get the negative or positive. It just means that it's to the east or the west of Jupiter. And then you would just page through this, gradually getting the data, and occasionally you would come across like a cloudy sky because these were taken from the ground, but you would keep going until you got enough data points to have a full orbital period, and then you would start working on the actual mathematics. So with that, I'm going to get into the actual lab and show you what it looks like. So back in the lab, I've showed you what the simulator looked like. Down here, it just goes through the spreadsheet again, but I've already explained all that. Now we're going to start making the plots. So if you're on a Windows or a Linux machine, I suggest you try to replicate these steps as best you can. You might need to fiddle around with it a little bit. If you're on a Mac, I can show you exactly what you need to do. So going back to your spreadsheet, I'm going to start with Io. So this is just the first tab down at the bottom. What you're going to do is you're going to click on either the top or the very bottom, whatever you want to highlight all of this data. So I'm going to click there, and then I'm going to do Shift, click, and it's going to highlight all of my data. From here, I'm going to go to Insert, I'm going to go to Chart, and I'm going to do an XY scatter plot. You then want to move your chart up here so that it's not blocking any of this text. And then I'm going to rename it, if it'll ever let me, Io, because that's the moon I'm doing right now. So then to get the exact kind of plot you're looking for, because the lab shows a plot that looks like this, it's got this nice line connecting all of it, you're going to right-click on your plot, you're going to click Change Chart Type, you're going to do an XY scatter, and you're going to click Scatter with Smooth Lines and Markers. Boom, done. Perfect. So this is what your plot should look like when it's all done. You can make it bigger or smaller, whatever you want to do. Get it out of the way of the text so that we can see everything without having to move anything. You want to make our lives as easy as possible because we have to grade all of this. So you're going to do this for all of these moons. I'm not going to do it for all of them. It's the exact same steps. So now, Let's go back to the lab and see what we need to do. Now you're going to answer some thought questions. Again, remember, thought questions are answer it. Give us what you're thinking. We're not going to mark you down if we disagree or anything. You get credit just for answering these. So number 1, look at all 4 of your plots. What do you notice about the differences in values on the x-axis? How do you think this difference will influence the orbital periods? So your x-axis is your time. So it's your observation step in hours. So for Io, it's kind of difficult to see because it's small, but it goes from 0 to 10 to 20 to 30. So if I were to do this for Europa as well, just to illustrate what this is talking about, this goes from 0 to 20 to 40 to 60, so it's in intervals of 20, whereas Io was in intervals of 10. So what does that tell you? That, Europa and Io look like they're both completing about 2 orbital periods, maybe, or 1 full orbital period, but Europa has significantly larger time jumps between data points. So what does this tell you? Looking again at all 4 plots, now consider the y-axis. What orbital parameters do you think is influenced by the maximum and minimum y values? Now, the y-axis is your distance from Jupiter and Jupiter diameters. So it's a measurement of distance. So Io gets up to a distance of about 3, it looks like. And Europa gets up to a distance of about 5, it looks like. So what does that mean? Which one's bigger? What does a bigger orbital distance from Jupiter mean? I keep going the wrong way. So then number 3, based on your answers to questions 1 and 2, which moon do you think is closest to Jupiter and which is the most distant? Now, you want to look at your plots to answer this, but I did already give you the answer earlier on when I was talking about I eat green cats. So, yeah, again, just a thought question. You won't be marked down for it. So now you're going to actually start your calculations. And all of these paragraphs go over exactly how to do that. I'm going to go over it with you too. So we're going to start off with Io. Let's go back to Io because that's just the first one. You're going to start in your period column with T1 and T2. What you want to do is you want to look at your values for your distance from Jupiter column. You want to find 2 values that are similar. Now, you have to be careful because you don't want to do this point on your chart and then this point on your chart. That is not 1 full orbital period. 1 full orbital period means it reaches its maximum and its minimum and goes back up to that value that you started at. So I would do this point and this point. So I would say this point is going to be this very first one, which corresponds to an observation step in hours of 0. So for T1, I would write 0. So for T2, I'm looking for this point. Whoops. T2, I'm looking for this point. Point number 42. That's not very helpful, is it? So I need to look for the value in the distance from Jupiter column that is closest to 0.98 after it has reached its maximum, and then it's gone down to the negatives and reached its minimum, and then come back up. So I'm looking for a 0.98, which looks like this one, which is 0.42, which is actually exactly what it told me, right? It told me series 1, 0.42. So 42. So then in hours, you're going to do T2 minus T1, which 42 minus 0 is just 42. Then you're going to convert this to days because this is currently in hours. So to do this in Excel, you're going to enter equation mode. So to enter equation mode, you click on the cell you want and you press an equals sign. Now you notice up here, this is the equation bar. This is where you can really type it in detail. In here, you're going to click on your 42 box. This tells it to take the value from the cell F23, F being the column, 23 being the row. So value from F23, and then you're going to divide that by 24 hours, right? How many hours are in a day? 24. So you have something in hours, you want to convert it to days, you divide it by 24, and then you press enter. And it gives me 1.75. So now I want to convert your unit, your measurement in days to years. So you're going to do the same thing. You're going to go down to your cell that you want, click on it, press the equals sign, go up to your equation bar, then you're going to click the cell you want to work with. This is F24 now. And I'm going to divide that by 365, right? There are 365 days in a year. I want to convert days to years, divide by 365. And then press enter. So now I've got 0.00479. Great, cool. You're going to do that for all of your moons. So that's exactly what it goes over here. To do your final calculation needs to be in years, so you convert hours to days by dividing by 24, and then days to years by dividing by 365. Now question 4, your first real question of the lab. Which of the Galilean moons has the shortest period and which has the longest? Now, keep in mind that these are going to be in decimals. If you want to look at the value in years, I recommend you just look at the value in hours because that's easier for my brain to comprehend. So like Io, say, has a period of 42. Let's say Europa has a period of 69. And then Ganymede has a period of 90. And then Callisto has a period of 110. Okay? Let's just say that the shortest period is going to be the smallest number, which is, for me, it's 42, so that's Io. So I would write Io equals shortest, however you want to designate it. And then the longest one I already know is Callisto with 110, so then I would say longest equals Callisto. Again, you have to denote it. You can't just say Io and Callisto. You have to say Io has the shortest, Callisto has the longest, or something. You can't just write down yes. You have to tell us what you're thinking. So then number 5, how do the orbital periods of the Galilean moons compare to the orbital period of the Earth's moon? And the orbital period of the Earth's moon is about 27 days. So going with 27 days, let's look at our shortest orbital period. It's already 42. So looking at the Galilean moons in general, do they all have orbital periods that are shorter than the orbital period of the moon? Or do they all have orbital periods that are longer than the orbital period of the moon? Now remember, this is in days. So we have to look at the one that's in days. So Io in days is 1.75 days. Moon is 27 days. Look at Callisto. Callisto is the one that has the longest orbital period. What's its orbital period in days? Are they all longer? Are they all shorter? Are some of them longer? Are some of them shorter? Which ones are longer? Which ones are shorter? Tell us about it. And then a thought question. Are you surprised by the orbital periods of the Galilean moons? If yes, why? And if no, why not? Now you're going to calculate the amplitude. So like I said, I would go over what the amplitude is. The amplitude is the distance from your x-axis, which for us is our time. The x-axis is always the one that goes horizontally. So it's the distance from this up to the peak or down to the trough in your wave pattern. So from here to here, or from here to here. Now, remember, the amplitude must be positive. So like it says here, if your amplitude value is negative because you were looking at a trough, then you have to take the absolute value to make it positive. So we're going to get our amplitude. Now, the amplitude of the wave corresponds to the semi-major axis of your moon, because this graph is showing the moon's orbit. When where it crosses the x-axis is where it's crossing in front of Jupiter. So let's say to my right is positive and to my left is negative. Then as it's starting at 0, goes positive, 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 reaches its maximum, comes back around, goes back down, reaches 0 again, goes past 0, back down to negative, 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 reaches its minimum, and then comes back around and does that again, right? So that's what we're graphing. So by looking at this amplitude, you're finding the distance, the largest distance that this moon reaches away from Jupiter. And that's its semi-major axis. So you can either look at your graph, find the point you think is closest to the maximum or the minimum. I would really recommend just going with the maximum. That way you don't have to deal with the absolute value. And then you write it down in this little box next to in Jupiter diameters underneath your semi-major axis, A. Or you can just look at your values. So I'm going to want to pick a point up here, the maximum point before it starts decreasing and going into negative. So I'm going to look for the maximum value somewhere in here. So I've got 2.3, 2.7, 2.9, 2.8. So 2.9 is going to be my maximum. So I will write down 2.95. And that'll be in Jupiter diameters, my semi-major axis, right? Because remember, this is already in Jupiter diameters. So now we need to convert that to AU. So to do this, you're going to multiply your amplitude by 9.545 times 10 to the negative 4. To convert it from Jupiter diameters to AU. So to do this, again, you're going to do an equation. So you're going to click on the box you want. You're going to do an equals sign. You're going to go up to your equation bar, click in that. I'm going to click my 2.95, and then I'm going to do asterisk, which is the symbol for multiplication. Then I'm going to do parentheses just to make sure that it multiplies this number by the entire next number that I give it. 9.545, and then the way you type it into Excel for an exponent, specifically for times 10 raised to the whatever exponent, is your number, e, and then the exponent. So for us, it's negative 4, so I would do 9.545 e negative 4, close parentheses, enter, boom, there's my number, 0.0028. Great. You're going to do that for all of your moons. And then you're going to look at which of the Galilean moons is closest to Jupiter and which is the furthest. So you're just going to look at your semi-major axis. You can look at the one in Jupiter diameters. You can look at the one in AU. Which one has the smallest number? Which one has the largest? Remember to designate. Then you're going to do thought question. The moon has an average distance from Earth of about 30 Earth diameters, pretty dang far away, or approximately 3 Jupiters. Why do you think our moon is closer to Earth than 3 of the 4 Galilean moons are to Jupiter? And the hint is, how does gravity pull depend on mass and distance, right? So you have to think about, we have this thing called gravity. It is dependent on how big your thing is. So if you have Earth and the moon, there will be a certain amount of gravity between them, keeping them bound together. If you have something much, much, much bigger than Earth, which is Jupiter, and then a tiny little moon, there's such a discrepancy between their masses, and they also have a gravity keeping them bound together. So just think about that. Why is our moon closer to Earth than 3 of the 4 Galilean moons? Now you're going to calculate the mass of Jupiter. We are in the home stretch. So this is the main equation you're going to be using. Remember, we went over this. Mass 1 equals the semi-major axis cubed of your moon divided by the period squared of your moon. And specifically, remember, A is in AU and P is in years. If you use the wrong value with the wrong unit, your answer will be wrong. So I want to calculate the mass of Jupiter. And I'm not going to input it in this box. I'm going to input it next to in solar masses. So the way you're going to do this, you're just going to use this formula. So I'm going to do equals to enter equation mode. Then I'm going to do my semi-major axis. And I'm going to do parentheses to make sure that it's dividing correctly. My semi-major axis A in AU is this cell. Raised to the power, which is a caret, you do shift 6. Raised to the power of 3, close parentheses, divided by parentheses, the period in years, raised to the power of 2. Enter. There's my mass in solar units. So you're going to do that for all of your moons. Then you're going to convert it to Earth masses to compare to like how big it is compared to Earth, right? Because this is telling us how big it is compared to the sun. So Io compared to the sun, the sun is, I'm thinking about how to phrase this. Io is 0.09% of the sun's mass. It's tiny compared to the sun. So now let's convert it to Earth masses. And to do that, you're going to divide your mass of Jupiter by the mass of Earth. So you're going to go into this cell, do the equal sign. You're going to select you're going to select the cell with your mass of Jupiter and solar masses. Click that. Then you're going to divide it by parentheses, so it divides by the whole number. 3 times 10 to the negative 6, aka 3e negative 6. Enter, boom. So Io is 323 times the size of Earth. No, I'm sorry, not Io. Jupiter is 323 times the size of the Earth. Because we're calculating the mass of Jupiter, not the mass of Io. So Jupiter's huge compared to the Earth. Now you're going to calculate your percent error. This is basically just how far off you are from the accepted value. So the accepted mass of Jupiter is about 318. This symbol, M, and then this symbol down here means Earth masses. Solar masses looks like this. It's an M with like a circled dot, and the Earth masses is M with a circle cross thing. So this is a more complicated equation. These bars are an absolute value. So the way you do this is you go to your percent error, you do your equal sign to go into equation mode, you do parentheses, then you do absolute value, then inside the parentheses of the absolute value, you're going to do your value in Earth masses. You're going to click your cell, minus 318. Outside the absolute value, you're going to divide by 318, close the parentheses, multiply by 100. So that's my percent error. I'm about 1.8% off, which is really not bad at all, right? 318 compared to 323, it's 5 masses difference. It's not bad. You're going to do that for all your moons. Please remember to take the absolute value. If your percent error is wild, like 70%, but your Earth mass, your mass of Jupiter in Earth masses is pretty similar to the accepted mass of Jupiter, then something's gone wrong in your equation. And please come to either my or Asmane's discussion section, and we can help you figure this out. So now you're going to look at your percent error measurements. Which of your mass measurements had the lowest percent error? Meaning Which moon had the lowest percent error? Io, Europa, Ganymede, or Callisto? Which one had the highest percent error? And then thought question, what do you think could have contributed to the error value? Meaning, where do you think your percent error came from? And then number 12, you learned an important lesson today. Scientists don't base results off of a single data point, but gather multiple measurements. Why do you think they do this? Give me your thoughts on it. How would we have been able to find the mass of Jupiter if we only had one data point in this orbit? I mean, one data point could be anything. You can't draw a line through one data point. You need at least two. So, yeah, what do you think? So now, last but not least, this is the very last section, I promise. We're going to put Jupiter in context with the Sun. Sometimes Jupiter is referred to as a failed star. If it was just a little bit bigger, it could have been massive enough to fuse hydrogen and be a tiny little star. So, using the moon from question 9 is which of your mass measurements had the lowest percent error? For my sake, I'll just use Io. So using the values calculated using Io, what is Jupiter's mass? That's what it means by its mass. What is Jupiter's mass in solar masses? Well, that's just this, 0.000971, whatever. So then I'm going to write 0.000971. How many times more massive would Jupiter need to be in order to become a small star? Think about it like an algebra problem. Mass of Jupiter, which you just had, times what equals 0.1. So the way to solve for this is you have 0.000971 times x equals 0.1. So then you can just move things around. So you can divide both sides by 0.000971, and you're left with x equals 0.1 divided by 0.000971. You just pop that into a calculator, and that gives you x. And so I'll just do that for you guys. Why not? Just pull up a Google tab and pop that in there. That's 102.99. So meaning Jupiter would have to be 103 times bigger in order to be a star. So it's really not all that close to being a star. So with that, you're done. So rename your file. Remember to submit both this lab document and your Excel file with all of your plots and all of your calculations. Remember to submit this too. And submit those to iCollege. And we will grade them. I look forward to seeing your results. Sometimes we get pretty interesting results with these calculations. Please remember to be careful about your parentheses and your exponents, and I will see you guys next time.